Now we're going to look at the integral test and the p-series test. Other than the geometric series and the telescoping series, we will not be able to find the sum to which an infinite series converges to. We will instead just concentrate on whether the infinite series converges or diverges. Just like integration problems, infinite series may require numerous techniques in order to determine whether or not the series converges or diverges. Let's look at the integral test. The integral test states that if a function is positive, continuous, and decreasing on the interval from 1 to infinity, then the series of a sub n converges if the improper integral a sub n from 1 to infinity has a numeric value, so it has to equal some number. If the integral is infinitely large, meaning if it goes to infinity, then the series will diverge. So let's determine whether the integral, or let's determine whether we can use the integral test. And if we can use the integral test, let's determine whether the sum of 1 over 1 plus 2n from 1 to infinity converges or diverges. First, we need to determine whether this function is, or this series is positive on the interval from 1 to infinity. In order to determine that, all you do is you plug in what happens when for f of 1, and at 1 you're going to have 1 over 1 plus 2n, or 2 times 1. This gives you 1 over 1 plus 2 times 1 gives you 1/3. 1/3 is a positive number. If the series is positive at 1, then it'll be positive at 2, 3, and so forth. So it's positive on the interval from 1 to infinity. To determine whether the series is continuous on the interval from 1 to infinity, we have to look at what numbers might make the series undefined. So because this is a fraction, we have to look at the denominator and see what makes the denominator equal 0. So we're going to take 1 plus 2n, set this equal to 0, and solve. So we're going to get 2n is equal to -1, and n is equal to -1/2. Since we're talking about the interval from 1 to infinity, this is where we have to be continuous, and what n cannot be is -1/2. This is outside the domain of what we're looking for, so it doesn't matter. And so it is continuous on the interval from 1 to infinity. To determine whether the series is decreasing on the interval from 1 to infinity, we use the first derivative test. Remember that the first derivative test states that if the derivative is negative within an interval, then the function is decreasing within that interval. So first thing we do is we take the derivative of the function. And so we want the derivative of 1 over 1 plus 2n with respect to n. I'm going to rewrite this first as 1 plus 2n to the -1 power. And now taking the derivative of this gives me -1, 1 plus 2n to the -2 power times 2, the derivative of the inside. Cleaning this up, we have -2 over 1 plus 2n to the second power. Now, in order to determine whether it is decreasing, we need to evaluate this derivative someplace within the interval from 1 to infinity. So let's evaluate the function, or the derivative, at, let's call it -2, something within 1 to infinity. So we have -2 over 1 plus 2 times 2, so let's say that's 1/4, or 4 being squared. Cleaning this up says we're going to have -2 over 5 squared is 25. So since we have a negative value here, since we've got a negative value, we know that the function is decreasing on the interval from 1 to infinity. Since the series is positive, continuous, and decreasing on the interval from 1 to infinity, we can use the integral test in order to integrate. So now we're going to take the limit of 1 over 1 plus 2n from 1 to infinity with respect to n. What we have here is an improper integral because we have an infinite limit, which means we need to rewrite this integral before we can integrate. Which means I'm going to remove the infinite limit, or I'm going to remove the infinite limit, and I'm going to take the limit from 1 to a on the function 1 over 1 plus 2n with respect to n as a approaches infinity. So now the integral is proper and we can integrate. Before we can integrate, we're going to need a proper strategy box. So u is equal to 1 plus 2n. du is equal to 2 with respect to n. We do not have 2 with respect to n, but that's okay. It's just a number and we can go get it. So we are going to take the limit as a approaches infinity. We need a 1/2 on the outside and a 2 on the inside, 1 plus 2n with respect to n from 1 to a. The integral is in shape to integrate now. We do have the du parts that we need. We have the 2 and the dn, and so we can integrate. This would be the limit of 1/2 times the natural log of the absolute value 1 plus 2n. This is not a plus c, it's a definite integral, and we're going to evaluate this as a approaches infinity from 1 to a. Now we're going to evaluate the f of a minus the f of 1. So we're going to take the limit as a approaches infinity. We're going to have 1/2 natural log of 1 plus 2a. And now I'm going to subtract 1/2 natural log, evaluating at 1 plus 2 times 1. Let's clean this up as much as I can. That gives us the limit as a approaches infinity. 1/2 natural log. Cannot clean up 1 plus 2a. It stays exactly the same. Minus 1/2 natural log. Here we have 1 plus 2 times 1. That gives us 1 plus 2. That gives us the natural log of 3. Now that we have taken, or now that we have evaluated, now we're going to take the limit. So applying the limit gives me 1/2 natural log of the absolute value of 1 plus 2 times infinity, which is infinity, minus 1/2 natural log of 3. The 1 plus infinity is just infinity. So I get 1/2 natural log of infinity minus 1/2 natural log of 3. The natural log of infinity is infinity, and 1/2 times infinity. So I get 1/2 times infinity minus 1/2 natural log of 3. And 1/2 times infinity is infinity minus 1/2 natural log of 3. The 1/2 natural log of 3 is nothing but a number, so an infinity minus some number gives you infinity. Since the integral of 1 over 1 plus 2n from 1 to infinity was equal to infinity, the integral diverges.